Okay, so this is 5.4, vectors. We're going to introduce vectors. We're going to talk about notation. We're going to talk about algebraic aspects and geometric aspects of vectors. We'll talk about a new operation, the dot product, that's kind of very different from other kinds of operations we've seen. And we're kind of setting up to be able to use vectors in 5.5. All right, so the idea of a vector is very simple. Usually in terms of the picture, we just draw it as an arrow, all right? And what is a vector? There's only two bits of information that a vector holds. Its length, or sometimes it's called magnitude, and its direction. All right. So this one, for example, the fact that it's pointing, roughly northeast, that's the idea of the direction. All right. So those are the only two bits of information that a vector holds. If I draw another arrow that has the same length and is pointing in exactly the same direction, then those two vectors are literally the same. They're considered the same mathematically, even though I'm drawing them in different places, all right? So for example, if I draw another vector right here, right, it has the same length, it's pointing in exactly the same direction, these two guys are equal. All right, so positioning of your vector, where you place your vector, is irrelevant when it comes to the actual vector itself. All right, so of course a vector that's different would be one that has different length, right? So this vector here is different from those two, or it could have different magnitude. Or it could have different direction, right? So maybe this one right here, it's different from all the other vectors I've drawn because it's pointing in a very different direction. And it could have, of course, different both, right? So this one has different magnitude and direction. Okay. So of all these vectors, these two are equal, and all these others are different from each other. All right. Notation-wise, we write vectors. Usually we like to use the letter V to denote vector. And we typically, when we write, we put an arrow on top of the V. All right. So something like that. All right. So we'll see in our class, we'll usually be using V, W, U for vector names. Of course, it doesn't matter. You can name your vector whatever you want, but typically those are the letters we use. All right, so in this way, we have a vector V here, and this one we said is pointing in the same direction. It has the same length, so this one is also V. All right, and all these other guys are different, so maybe let's just give them names. Maybe I call this one W, maybe I'll call this one U, and let's call this one S. All right, so these U, W, and S are all different from V and from each other as well. Okay, so the concept of a vector is a very, very simple idea. But it's immensely powerful because once we start working with actual physical objects, or for example, physical motion in the real world, you're going to need vectors to describe that motion, right? So, for example, when we talk about the concept of speed, usually we just say 50 miles per hour. But if you actually want to have even more information, you could say, I'm driving 50 miles per hour northwest, right? Or I'm driving 30 miles per hour south. So those two together, the 30 miles per hour would be, let me draw this, 30 miles per hour would be describing the magnitude of a vector, and then south would be describing the direction. All right. So when we talk about motion, the concept of the vector is very, very integral to studying that motion. And again, another example, if I'm driving 50 miles per hour northwest, right, I can represent that as a vector, pointing in that direction, 50 miles per hour. Let me try to draw to the same scale as my previous example, so a little longer, right? So length 50 to denote 50 miles per hour, and then it's pointing northwest, which denotes the direction in which I'm moving. All right. So if you do go on to take more math, calculus, and especially physics, vectors are just ridiculously important because they do help us describe the real world. So if you're, let's say, if you're looking from above, let's say from Google Maps, you see a road like this, and you have a car driving along this road, right, from above again. The correct way to describe your velocity is as a vector, just like these two that I've drawn here, 30 miles per hour south, 50 miles per hour northwest. Here you have a car, it's driving in that direction at this moment on the road, and that would be its speed. All right, if later on it's here, it would be driving in that direction, and this would be its speed. Okay. So technically, I mean, in practice, right, outside of physics or math, the word speed and velocity we use interchangeably, but in kind of in a more scientific context, you would use speed as just the 30 miles per hour, right, the 50 miles per hour, and the word velocity would include it with the information about the direction. All right. Okay, so that's just one small example of where you can see vectors. Another example is when we talk about force. So if you're on Earth, let me draw the Earth here, all right? And you have a spaceship up here, right? Rocket ship. Then there's a force, the force of gravity pulls you towards the Earth, right? You have the sun over here. The force of gravity also pulls you towards the sun, right? Now, vectors describe this very, very well because the length of the vector would describe how hard this object is pulling you, right? The sun is pulling really hard because it's very massive, right? So it's kind of a force of gravity that comes from the sun is very powerful, so very long, whereas the Earth is smaller, so perhaps this arrow is smaller. All right. The direction of the arrow indicates which direction you're being pulled, right? And in this case, it would be you're being pulled towards the center of the Earth, and in this case, with the sun, you would be pulled towards the direction of the sun. And of course, the magnitude of these two vectors would depend on how far you are away from either the sun or the Earth. Okay. So actually, if you are very, very close to the Earth and very, very far from the sun, the Earth force vector would be a lot bigger, right? It depends on the exact setup, exactly where your spaceship is. In the next section, we'll talk about the same type of situation, but a little more pedestrian. You have so one of the examples you'll see in the book is you have a horse that's being pulled by two people, right? This person here. So here's your horse viewed from above, let's say, right? You have two people, they're pulling the horse, pulling that direction, right? And maybe this person is pulling with this force, and this person is pulling maybe with that force, right? So this guy on top is pulling harder, right? And he's pulling in this direction, kind of northeast-ish. And this guy on the bottom is pulling not as hard, and is pulling, southeast-ish, right? So one question would be, if the horse doesn't want to move, what direction should it resist these two people's pulling, right? And it turns out it's going to be something like it should resist in this direction and with a certain length, all right? So again, very, very useful when you're talking about forces of any kind, right? Force of gravity, force of, pulling on a rope, springs, anything involving force is very likely to involve vectors when you're talking about 2 dimensions, 3 dimensions, the real world. Okay, one last example is if you're talking about, again, velocity, but let's say a river, right? So you have a river like this, and then you can describe how fast the water is moving and in what direction at every point using a bunch of vectors, right? So these would indicate at this point, the water is moving in this direction. How fast is it moving? The length of that vector, right? So perhaps maybe there's a rock in the middle of the river here. And so the water would be kind of diverted like that, right? So if you draw a lot of these, you can see kind of the overall kind of motion of this river. All right. So if you ever look at weather maps or the weather, you'll often see exactly this kind of picture for wind, right? Where you have little arrows indicating the direction of the wind, and the length of the arrow indicates how fast the wind is blowing. So again, in this situation, the vectors are again describing velocity, but kind of used in a much more advanced context where you're working with many, many vectors all at once. All right. Okay, so now that we kind of have at least some idea of why we care about these things, let's talk about some geometry of vectors, and then we'll talk about the algebra of vectors. We'll talk about notation, and then we'll talk about the dot product, which is a very interesting kind of feature that is somewhat different from kind of the arithmetic that we've seen in the past. Okay, so geometry. So this is a math class. So if we have a new mathematical object, one thing we always like to ask is, can you kind of have these objects interact with each other mathematically? And in particular, we can ask, if I have two vectors, can I add them? Can I subtract them? Can I multiply them? Right? What kind of operations can I do if I have two vectors? Right? So let's start with addition. And for now, we're working with geometry, so I'm going to do everything in terms of pictures. But all of this stuff that we're going to talk about here in this geometry section will extend to algebra, where we're going to be able to work with quantities instead of pictures, all right, with algebraic quantities. All right, so addition. So in terms of the picture, how do we add two vectors? Very simple. If I have a vector like this, and I have another vector like this, let me call this one V, let me call this one W. The way we add them is, well, there's two ways to think about this, or to describe this, and they're both equivalent. They both give the same answer. The one that's perhaps more approachable initially is like this. So V plus W is the vector where you draw V first, and then you, at the tip of V, right, at the head of V. So one thing, we often call this point here the tail, and this one we often call the head, all right, of a vector. Let me draw it again just to have this in a separate picture. So we draw V, right? So again, it doesn't matter where we draw it. So let me just draw it. As long as this length is the same as this length, and this direction is the same as that direction. So this still represents V. Okay, so we draw V first, and at the head of V, we draw W. We start with the tail of W there, and then we draw W like that. All right. So if I do look at this, then if I start at the tail of V and I want to end at the head of W, I can draw a vector that looks like that, right? Again, starting at the tail of V, ending at the head of W, that's going to be V plus W. All right, that's how you add two vectors. That's the definition of adding two vectors, at least a picture version of the definition. All right. Okay. So very straightforward. And one thing nice about this definition is that when I want to add vectors, when I have addition, right, the order usually doesn't matter, right? So normally with addition, 3 plus 5, that's equal to 5 plus 3, right? Order doesn't matter. In this case, the way we define the addition of vectors, that's still true, right? Because if I travel W first, so let me do that actually. Let me draw them both simultaneously just to emphasize that they're the same. So here's V, here's W, right? And we've already said that this guy right here is V plus W. Okay? All right, now if I happen to draw W first, it's going to look like this, and then I draw V like that, then the vector that starts at the tail of W and ends at the head of V, that's going to be W plus V. All right, but if you think about this and you use a little bit of geometry, these two vectors are the same. And essentially, it's because this is a parallelogram here. This length is the same as that length, and this length is the same as that length. And so we have a parallelogram, and that is, in effect, what causes V plus W to be the same as W plus V. All right. So here, in a way, we've spent a bit of time kind of describing something that is obvious for numbers. But of course, if you're going to make up a new concept of addition, right, you have to check whether the usual concepts of addition still apply. All right. So that's how you add geometrically. That's one way to, at least one way to think of it. There's another point of view which is often very useful as well. So this point of view is very useful when oftentimes when you think about when you're working kind of with velocity, because one way you can think about this is you're driving a car 50 miles per hour, so that would be like my V, and you drive 50 miles per hour, and then you turn and then you drive 30 miles per hour, right, as your W. So this would describe kind of in a way your driving trip, right? The sum of these two vectors. This is very, very loose. That's a very loose idea. But oftentimes, we don't necessarily want to think of vectors as kind of being consecutive, like one after the other. And so that's where the second idea of addition of vector comes from. And that's where, again, let's say we have V here and W like this, right? So in this second method of addition, I'm going to take V, I'm going to take W and draw them both with the same tail. All right, so here's W. Okay, I do this, and then I fill in this parallelogram right here, like that. All right, and V plus W is going to be the diagonal right there. Okay. Now, of course, these two ways of adding are the same, because if you think about this, right, this red dotted line over here, that's actually W, right? It's parallel to the W on the opposite side. And then this red one here is actually V, right? So you can think of this as, if you think about our original way to add, right? You go V and then you go W, or you go W and then you go V, right? That's the same as putting V and W with their tails together and drawing that diagonal. All right. So this point of view is very useful when you're talking about forces acting on an object, like that horse example, right? If this is the horse, we have it's being pulled in that direction and it's also being pulled in that direction simultaneously. So oftentimes you want to draw the forces in the same place, because to represent the fact that the forces are acting on that object right there, right, on that horse. Okay, so that's how we add. Fairly straightforward geometrically. Let's talk about scalar multiplication. So that's our next operation, and this one is in a way different from regular multiplication because of this word scalar. Scalar means number. All right, so number like 1, 2, 3, 1/2, 1/3, pi, minus pi, and so on. Okay, so scalar is in contrast to, so let me write here, number in contrast to vector. All right, because a vector is not a number. A vector is a length or a magnitude and a direction. Okay, whereas a scalar is just simply a number. Okay, so when we say scalar multiplication, what we mean is we're going to right now describe how to multiply, so that's the multiplication part, a scalar, so how to multiply a number to a vector. All right. Okay, so for example, if I have a vector like this, v, right, the question is what is the vector 3v, or 3 times v, right? So let me write like this, 3 times v. Okay, normally we just write that as 3v, all right? But the question is, what would that be? And in terms of the geometric picture of vectors, is very simple. 3v would be the same exact vector pointing in the same direction, except 3 times longer. All right, so if this is one length of v, this is a second length of v, this is a third length of v, this guy right here would be 3v. All right. So same length, but same direction, but 3 times the length. All right, in the same way, if I want to talk about 1/2 v, that would be vector in the same direction as v, except only half the length of my original v. All right, let me kind of draw it like this, 1/2 v, and then let me put dotted lines to indicate what v would have been. Okay, so 1/2 v. All right. So the important thing is only the magnitude changes for these two examples, but we can also do -1 times v, all right? And that's typically written minus v. What does that do? Well, it actually takes our v and keeps its length the same, but flips the direction to the opposite direction, all right? So if v was this guy here, then minus v would, let me do it kind of be a little consistent with the example above. So let me draw v in red. Then minus v would be in that direction. All right, exactly, precisely the opposite direction, except, precisely the opposite direction and exactly the same length. All right, so whatever length the original v is, minus v has the same length. All right. If I want to do something like -3v, or let's say -2v, then what I would do is I would take my original v. I would, so the minus means flip the direction, and then the 2 means lengthen it by a factor of 2. So it would be 1 length of v, second length of v, and again, pointing in precisely the opposite direction. So this is -2v. All right. Okay. So next you might think a couple things. One question is, what about subtraction? Right? And the fun thing here is, in a way, there's no such thing as subtraction, even with regular numbers. Because anytime you subtract, let's say just with regular numbers, 7 minus 5, you can think of that as addition like this, 7 plus -5, right? And -5 is the opposite of 5, right? It's in a way the opposite of 5. So anytime you have subtraction, you can rewrite it as kind of like an addition and then a negative of the other thing, right? And in this case, negative, you could think of this as multiplying 5 by -1. All right, so for vectors, same thing. So we don't actually have to describe subtraction separately. We can say if I have two vectors v and w, let me draw them again. So let's say this is v, and let's say this is w. Then v minus w is going to be the vector v plus -w. All right, and this is a great way of describing it because we know how to add vectors. We just talked about it. And we know how to do scalar multiplication of vectors. We just talked about it, right? And so automatically, this concept of subtraction is defined for us, all right? So again, in a way, there is no such thing as subtraction. This minus sign right here is, in a way, you can think of it as a shorthand for this right-hand side, all right? Okay, so in practice, how would I do that? Well, I would take the vector v, draw it right there. I would take the vector w, except I flipped the direction because I'm talking about minus w. So like that. All right, and let me kind of emphasize this by writing w is in exactly the opposite direction. This one, sorry. So this is minus w here, and this is my v. And then v minus w is exactly v plus negative w. So it's going to be this one. All right. Okay, let me actually put this over here. Sorry. Let me put this over here. Okay, so that's one way to add, to subtract two vectors. But you can take another point of view where you can draw v and you can draw w, just the regular w. So let me again do that in red here. Right, here's the regular w. Then v minus w, right, is the guy that when you add it to w gives you v, right? So v, let me write this down, v minus w. What vector is this? It's the vector that when you add it to w gives you v, right? So what, in terms of this picture up here, what do I add, what do I need to add to this guy down here to give me v? Well, it has to be this one right there, right? This w plus this vector is equal to v, right? So that means that that vector has to be v minus w. Okay, so that's another way to think of subtraction. Again, let me kind of draw it by itself. We have v here. We draw w like this. V minus w is the vector that it starts at the head of w and goes to the head of v, like that. All right. And again, the main point is that w plus v minus w, right? So that would be traveling from here to here and then here to there should be equal to v, which it is. Okay. So that's just a separate secondary way you can think of subtraction. Of course, they're literally the same because if you think about this again, we have parallelograms here, so everything kind of matches up exactly the same. Okay, so subtraction is not a big deal in that we don't need to kind of create a new idea of subtraction. The next one we might think about is multiplication, right? We had scalar multiplication, but what about just regular multiplication? Can I take two vectors and multiply them, right? Take their product? And the answer is no. All right, so there is no concept of multiplication of two vectors that behaves exactly like the concept of multiplication that we're used to. So what we're going to do is we're going to talk about a concept of multiplication of two vectors that behaves pretty much like multiplication, but not exactly. And that's going to be called the dot product. We would never, ever actually say the words multiply two vectors. So we want to be very careful about that. All right. So in a few minutes, we'll describe what the dot product is, but we always use the word dot product when we talk about it. We would never say multiplication. All right. So there is no good concept of multiplication of two vectors, and there is definitely no concept of division. Okay. So let me write in a few minutes dot product. And if you do go on to take more math, in the future, if you take calculus or vector calculus, you'll be talking about the cross product, which is another way to multiply two vectors. But we're not going to discuss it in our class. All right. So at this point, right, we can add, we can subtract, we can scalar multiply vectors, but only if we have pictures, right? So in real life, right, most of the time you don't have pictures. You're working with formulas, right? You're working with kind of mathematical expressions that involve actual numbers and stuff like that instead of pictures. And usually you don't even want to work with pictures because pictures can be inaccurate and misleading, right? So our next step is to talk about the algebraic aspect of, or let me write algebraic point of view. All right. So we're going to talk about, again, exactly the same stuff, addition, scalar multiplication, except from an algebraic point of view, which will allow us to actually do computations in a typical setting, right? Or in a setting where we don't have pictures. Okay, so the first thing is, before we even start this, let's notice that because a vector is only determined by its direction and its length, that means we can move a vector wherever we like. And so that means if I have an axis like this, right, an xy axis, then if we're working with a vector like this v, I can always move this vector so that its tail is at the origin, like that, right? And again, I want it to be the same vector, so same length, same direction, except I've just shifted it so that its tail is at the origin. All right, so this is what we call standard position. All right, so any vector that we want to work with, we can shift it to the origin, right? And once we've shifted, its tail to the origin, and once we've shifted its tail to the origin, we say it's in standard position. And this is really important because once a vector is in standard position, then we can actually describe it without having to draw pictures, because the position where its head is at, like let's say that position here is in terms of coordinates. Let's say that's 3, 1, right? Then this number 3 and that number 1 completely describe the vector, right? So in other words, if I say in words, I'm working with the vector whose head is at 5, 2 in standard position. When it's in standard position, its head is at 5, 2. There's only one vector that could be, right? That would be the vector where 1, 2, 3, 4, 5, 1, 2, right? It's in standard position, so its tail has to be here. Its head is at 5, 2, so its head has to be there. And so this is the only vector, right, that could be. So the two numbers, 5 and 2, completely determine the vector that I'm working with, all right? And so this is the basis of our algebraic discussion of vectors, the fact that any vector can be described with just a pair of numbers. And again, this is always assuming that we've placed it so that its tail is at the origin, all right? So in fact, our notation for vectors in this algebraic setting comes directly from the 3, 1 and from the 5, 2. So this vector over here, v, the way we would write it is v equals, and then we're going to use sharp brackets, or at least our book uses sharp brackets. There's a lot of different notations. Many different books will have different notations, but the one we have is sharp brackets, so we'll stick with that. 3, 1, like that. All right. So the sharp brackets reminds us that we're talking about a vector. So that reminds us that this thing represents a vector. All right. Whereas the parentheses tells us we're talking about a point. Right. So they seem very similar. They both have the 3 and the 1 in there, but it's very important to know the distinction of when you're working with a vector versus when you're just talking about a point in space, right? Because a vector is, a point, is a direction, right, and a length, whereas a point is just a position in space. Okay, so it's a much simpler concept. All right, so this vector here, this 5, 2, let me call it W. The way we would write that is W is equal to sharp bracket 5, 2. All right, our book uses this notation where they call, so let me do this. Let me draw V down here again. So here's v. All right. It's the vector 3, comma 1, right? Notice something very interesting here, or yeah, interesting, I guess. If I take this horizontal vector like this, that ends right there, and then I take this vertical vector that goes up like this, where I have a right angle right there, okay? Then v is the sum of these two vectors, right? Just from our definition of adding two vectors, right? This guy plus that guy is equal to v. Okay, just from our definition of addition. So what happens is any vector that we have, we can break it down as the sum of a horizontal one, a horizontal vector, and a vertical vector, right? So our book likes to call this v sub x and v sub y, right? So this guy is horizontal. That's the important feature of it. And this guy is vertical, right? And them together, vx plus vy is equal to my vector v. Okay, this is a really important breakdown of v, because in a lot of settings, what we would like to do is work with v or something like v, but it's kind of complicated, right? In this case, it's 3, comma 1, which is kind of complicated. But what we can do is we can break it down into two simpler pieces, vx and vy, and they're simpler because each of those are, for example, vx is just horizontal, right? Vy is just vertical. And so you can study v by studying vx and vy in a way separately. All right. So this is a very important breakdown of a vector. And later on, we'll have some notation that for a second notation for vectors that incorporates this idea. All right. By the way, if we did want to write down exactly what v sub x and v sub y were, v sub x would be, well, because it's horizontal, right, and it ends right there, and v's horizontal length is 3, and its kind of vertical portion is 1, v sub x, notice it should be 3, comma 0, and v sub y, because it's vertical, it should be 0, comma 1. All right. Okay. So this is a small note. We'll use this again in just a few minutes when we have a secondary notation. All right, let's see. Let me give one more example, because all of my examples here have been like +3, +1, right? So obviously you could have vectors which point in negative directions. So this vector right there perhaps is -2, comma -3, right? Perfectly legal. Sorry, +2, -3, because it's positive x coordinate right there and negative y coordinate. This guy right there might be -4, comma -5, right? This one right there might be -2, comma 1. All right. So you can certainly have vectors pointing in whatever direction you like, and of course that will affect whether these entries are positive or negative. Okay, so now that we have this kind of algebraic description of vectors, let's talk about how to connect the two descriptions, the geometric and the algebraic description. So what I mean is, if I have a vector v, let's say again, this is 3, comma 1 equals v, right? We said a vector is a length or a magnitude, length / magnitude, and a direction. So knowing that it's 3, comma 1, how do I actually figure out that length? And how do I describe that direction? So again, we draw the picture in standard position. And we notice that, again, if I drop this perpendicular down, right, this length here is 3, right? That height here is 1, right? Literally, that's the definition of that 3, comma 1 right there. And so what we have is a right triangle. So this hypotenuse, which is the length of my vector, I can figure it out, right? It's 3 squared plus 1 squared square root, which in this case is going to be square root 10, all right? So in this example, length of v is equal to square root 10. All right. So again, the point here is if I give you, a vector 4 comma 10, you can always figure out its length. All right. Now, what about its direction? So we can also describe its direction because the direction is given by this angle right there, right? If I tell you that that angle is whatever degrees, then you always know what direction that vector is pointing, right? If I tell you that the angle from the x-axis of the vector that I'm working with is pi over 2, right? Then that means I'm working with a vector that's pointing straight upwards, right? If I tell you the vector that I'm working with has an angle with the x-axis of minus pi over 4, that means I'm talking about that vector right there. All right. Or not that vector, but the vector that points in that direction, right? I haven't told you the length yet. Okay. So the point here is that the angle with the x-axis completely describes the direction aspect of a vector. All right. So if I give you this 3 comma 1 description as for v, the question is what exactly is that angle theta? And again, here's where actually the trig comes in. Tangent theta is equal to opposite over adjacent, right? And so theta is equal to arctangent 1/3. Okay. So in this way, we can describe both the length and the angle or the direction of a vector if given its description, its kind of algebraic description. All right. Okay, before we move on, one small bit of notation. The length of v, we don't want to have to keep writing that. So the notation for the length of v is v absolute value. Okay. So the absolute value gives you, absolute value of a vector is a number, and that number is the length of the vector. Okay, so this was, this example here was where I gave you v is 3 comma 1, and I figured out the length and the angle. Obviously, you could go the other way as well. If I tell you that we have a vector whose angle here is pi over 6, right? And whose length here is 10, then the other direction would be, this is what comma what, right? And this is really useful because, again, if you're given a vector in terms of the geometric aspect, its magnitude and its direction, then we would like to be able to kind of work with it algebraically, which is going to require these two numbers here. Okay. And again, this is where our trig comes in. We have pi over 6 here. We have right triangle, right? If I drop that guy down. And so we know cosine of pi over 6 is equal to adjacent over hypotenuse, right? Let me just write them out. Adjacent over hypotenuse, right? And so that's going to be equal to adjacent over 10. But what is adjacent? Adjacent is exactly this length right there, right? And that's exactly that number that goes in the x-coordinate, okay? So in particular, what that means is that, let me do a little bit of algebra here, right? Adjacent is equal to 10 times cosine pi over 6. Cosine pi over 6 is root 3 over 2. So 10 root 3 over 2, so 5 root 3. Okay. So what we figured out here is that entry is 5 root 3. All right. And in exactly the same way, sine of pi over 6 is opposite over hypotenuse. Our hypotenuse is 10 again, right? Opposite is exactly that vertical length right there, right? And that, of course, represents the y coordinate. So that's exactly the second coordinate right there. And so if we just, again, do the same kind of algebra, opposite is equal to 10 sine pi over 6, which is 10 of 1 times 1/2, which is 5. Okay. And so this entry right there is 5. All right. So in other words, the vector whose length is 10 and whose angle with the x-axis is pi over 6, that's equivalent to the vector 5 root 3, comma 5. All right. Okay. Sometimes it'll be, like we said, very useful to work algebraically like this, but sometimes it's very useful to understand the vector in terms of its angle with the x-axis. So we'll be doing both in our class, especially the second one, because our class is trig. So we're particularly interested in kind of this, in a way, trigonometric description of the vector, right? As in terms of the angle. All right. By the way, a bit of notation. This pi over 6, our book likes to call the direction angle. All right. So let me draw another picture down here because that one's a little messy. If I have a vector like this, that theta right there, our book calls it the direction angle. That's not standard notation or standard terminology. But it's the terminology that our book uses, and you'll probably see it in the homework. All right. By the way, this entire discussion here, we're going to go through in a way again when we talk about complex numbers, because the way we look at complex numbers visually is going to be in the plane as well. And it's going to be really important to understand the angle of a complex number with the x-axis. We'll spend an entire section on that. Okay. Let's talk about addition and subtraction. Or sorry, addition and scalar multiplication. And of course, by extension, that means we're going to be talking about subtraction as well. So how do I add two vectors that are given in kind of this algebraic form, 3, 1 plus 2, 6? How would I add them? Right. Well, if we think about how this would happen geometrically, we can figure it out very easy. 3, 1 is 1, 2, 3, and then comma 1 up. So this would be the first vector, 3, 1, right? So this guy here is 3, 1. Okay, if I want to add this to 2, 6, the way I would do that geometrically is I would draw 2, 6 starting from the head of 3, 1, right? So right there, I would draw 2, 6, so 2 more spaces to the right, and then 6 spaces up. 1, 2, 3, 4, 5, 6, right? So this would be from here all the way up to there, right? 2 more spaces to the right. I've already moved 3 spaces. 2 more is going to be, so let me indicate it like this, 3, and then 2 more would be 5, right? In terms of the vertical, I went 3, 1, so this was 1, and then I added 6 more upwards, so that got me to 7. Okay, so ultimately what I see is the sum, right, is the vector that goes from the tail all the way to the head. And what is that? Well, that position right there is exactly 5, 7, right? So this sum vector right there is 5, 7. Okay. And what's 5, 7? Well, if you look at this 3, 1 and 2, 6, it's this 3 plus the 2, and then the 1 plus the 6. All right. So as it turns out, adding vectors is really, really simple, right? 5, 10 plus 2, minus 3 is going to be 5 plus 2, 10 minus 3. So that's going to be 7, 7. All right. And again, up here, this was equal to 5, 7. All right. And so adding vectors is super, super simple algebraically, right? Even geometrically is a little complicated. You have to maneuver the vectors around. right? Stuff like that. Here, all you have to do is be able to add two numbers. Okay, so minus 3 comma 0 plus 4 comma 10, that's going to be 1 comma 10. All right. Okay, scalar multiplication is just as simple. If I have a vector, let's say 3 comma 1 again, right? How do I scalar multiply? So for example, what would 2 times 3 comma 1 be, right? And again, this is scalar multiplication. You have a scalar here, 2, and you're multiplying it to a vector here, 3 comma 1, right? So this is a scalar, and that guy's a vector. And so that means this, this is scalar multiplication. Scalar multiplication. Okay. So what would it be? Well, in terms of the picture up here, this vector is 3 comma 1, which means I'm moving 3 spaces to the right and then 1 space up. Well, if I have 2 times 3 comma 1, that means I move another 3 spaces to the right, oops, and another space up, right? So that would be this guy here, right? Double the length. And what is that? Of course, that's 6 comma 2, right? So this vector here, 6 comma 2. And so, of course, if you think about this, this is just 2 times 3, 2 times 1, right? So 6 comma 2. So what happens is multiplication is really, really simple. What you do is, or scalar multiplication is really simple. You just multiply whatever your scalar is into each entry. So 4 times 2 comma 7, right? This scalar multiplication of 4 with the vector 2 comma 7 is 8 comma 28, right? And this works for negatives as well. Minus 2 comma 7 is negative 2 comma negative 7. And that makes sense because if 2 comma 7 is here, right? Negative minus 1 times 2 comma 7 should be the vector that points in the opposite direction. And how do I get the opposite direction of this guy here? Well, if I move 2 steps to the right and 7 steps up, the opposite direction is 2 steps to the left and 7 steps down. Okay, so minus 2 comma minus 7. It fits perfectly. The algebraic and geometric aspects of a vector fit perfectly together. Okay, and of course, minus 3 times 4 comma 0 is minus 12 comma 0. All right, so scalar multiplication is very simple. Okay, what about subtraction then? Well, again, we don't really have to talk about it because if you have addition and scalar multiplication, then you have subtraction, 3 comma 1 minus 2 comma 10. You can think of that as 3 comma 1 plus minus 2 comma 10, right? And if you did think of it that way, then you would get 3 comma 1 plus minus 2 comma minus 10, which would be 3 minus 2 comma 1 minus 10, which is 1 comma minus 9. All right. Okay, again, here I'm just emphasizing that you don't need to define the concept of subtraction once you have multiplication and once you have addition and scalar multiplication. But colloquially, right, usually when we think of subtraction, we just think about 3 minus 2, 1 minus 10, right? And of course you get the same answer. Okay. All right. So this was the adding, scalar multiplication and subtraction when we're describing vectors with in this way with the sharp brackets, right? In terms of their position of their head. Notice that we're not going to be talking about addition in this aspect when we have theta here like this and we describe the length here like that, because it's not that easy. All right, because if I did want to add another vector like this, then this vector here, its angle would be described like that, right? Always angle with the its direction angle is the angle with the horizontal, right? So if this is theta, maybe call that alpha. Then the angle of the resulting sum is actually not going to be theta plus alpha. So it's actually a lot more complicated than that. So we're not going to be describing addition in this geometric description, or in this kind of description of vectors. But scalar multiplication is no problem, because all you're doing is you're changing the length, or you're changing swapping the direction to the opposite side. In which case, one way you can describe it is to add 180 degrees or pi to your angle, right? So if this angle here was pi over 6, then you add pi, that gives you the angle, the arrow that's in the opposite direction. Okay, just a couple more notes, and actually what I'm going to do is I'm going to end this video, and then I'll talk about I'll continue this in a second video where we start talking about the dot product, which is immensely important. All right, but the last two couple notes here is number one, just notational. So v plus w. When we add two vectors, oftentimes this guy is called the resultant of v and w. Right, so resultant just means the sum. All right, it's not used in math too much, pretty much never, but in physics it's used quite a bit. So you might want to remember that term if you are going to be taking physics. And we'll see that term in the applications of vectors for our class in the next section. All right, and number two, there's one exception to our definition of vector, So what we said a vector was a length or magnitude / magnitude, same thing, and direction, right? But there's actually one vector that is an exception to this, and that's the zero vector. So I'm going to indicate it like this, zero vector, right? So that's a zero there with an arrow on top, all right? So remember, we always want to put arrows on top because we definitely want to always know whether we're working with a vector or a number, right? And numbers don't have arrows on top. So if I'm talking about the zero vector, so that would be the vector of zero length. Right? I always want to indicate that, I always want to indicate that I'm working with a vector with an arrow. Okay, so this guy has zero length, so actually its direction is irrelevant, right? So there's no direction. Right, so the zero vector is the one vector that has no direction. Just because direction doesn't even make sense if you have zero length, right? But the zero vector is important, of course, because whenever you talk about arithmetic, right, addition, subtraction, and in this case, scalar multiplication, the concept of zero is important because, well, when you have two vectors that are opposite to each other, when you add them, you should get nothing, right? So that's indicated by the, or that's represented by the zero vector, right? Or if you have a vector and you multiply it, scalar multiply it by zero, then you should end up with a vector that has no length, right? And so that's represented again by the zero vector. But that's our only exception to kind of our description of vectors. All right, so I'm going to end this one. I'm going to do the second half of this section in a second video.